Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face Trending List, published on January 20th, 2026, about 6 days ago. It introduces a novel dual-stream architecture that helps robots learn fine motor skills without forgetting their general visual knowledge, improving success rates on the simpler ENV benchmark to 62%. The paper is titled TwinBrainVLA, Unleashing the Potential of Generalist Vision Language Models for Embodied Tasks via Asymmetric Mixture of Transformers. And, as we'll see later, the performance gains on complex manipulation tasks are really impressive. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 illustrates the core architectural shift. On the left, the standard vanilla VLA uses a single, monolithic backbone for everything. This model is fully fine-tuned, indicated by the fire icon, which risks overriding general knowledge with specific motor skills. On the right, TwinBrainVLA decouples these roles. It keeps a frozen left brain to preserve semantic understanding, while a trainable right brain handles physical control. The connecting arrows show how the specialist side dynamically borrows knowledge from the generalist side. Figure 2 details the complete TwinBrainVLA framework. In panel A, the frozen left brain processes vision and text, while the trainable right brain adds the robot's physical state. These streams condition the action expert, which uses flow matching, a generative method for continuous data, to produce smooth robot controls. Panel B zooms in on the asymmetric mixture of transformers mechanism. It shows how the trainable layers attend to frozen key-value pairs from the generalist model, fusing high-level semantics with low-level motor skills. Table 1 reports the performance on the simpler ENV benchmark using a Widow X robot. The columns define 4 manipulation tasks, such as putting a carrot on a plate or stacking blocks, which test the model's precision. The upper section lists over a dozen baselines, including Octo and Isaac Groot, which struggle with the harder stacking task. In contrast, the bottom rows show that TwinBrainVLA achieves the highest average success rate. With the QN3 backbone, it reaches 62%, beating the best previous model by about 5 points. So, while the previous table focused on simpler ENV, Table 2 shifts to the RoboCasa tabletop simulation using the GR1 robot. The rows list over 20 specific pick-and-place tasks, ranging from moving a bottle to a cabinet to placing milk in a microwave. When we check the baselines in the middle columns, models like Isaac Groot and Quen Groot average around 48% success. In contrast, the far-right columns revealed that TwinBrainVLA with the QN3 backbone reaches 55%, confirming its robustness across diverse scenarios. Alright, digging into the implementation details, this figure displays the prompt templates that steer the two hemispheres. The top section lists the system prompts. Notice that the left brain is simply told it understands images and texts, keeping its role general. In contrast, the right brain is explicitly instructed to process robot states and take action. Then, the bottom section shows the user prompts, where the right brain receives specific details like the robot type and a command to predict the next move. So to wrap things up, TwinBrainVLA effectively resolves the conflict between general reasoning and specific motor control. By structurally decoupling these functions, it prevents catastrophic forgetting and points toward a future where robots are both cognitively smart and physically dexterous. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.